Start. Okay, so yesterday, I just gave you some perspectives and overview of extreme value statistics. So why is it important to study extreme value statistics and so on. And I will work out the details. And I said there are two models that people normally look at. And one is this when the variables are independent and identically distributed, IID model. And the second, which is sort of in physics, it's analog of ideal gas in some sense. And the other one is the random walk model, which is strongly correlated. So there are two examples we discussed. And so today I want to work out start working out the details of the extreme value statistics for both models. But before that, I thought I would just, make a small recap of some basic things about, random variables and their distribution so that we are all in the same page. Just to remind you, you all know about this, but just so that we are talking about the same language, okay? So let's first, so this is just an appendix if you like. So let's think of a single random variable. X, and suppose that it's distributed. So random variable means that its value fluctuates from one sample to another sample, and it has a PDF distributed via the probability density function, let's say f of x. And this f of x, for simplicity, you can think of this as a symmetric function. And it's normalized to 1. So I gave you a few examples. Let me recall, the one which normally we come across often. So this is the standard Gaussian distribution with zero mean. And this L naught is just some length scale so that this is dimensionless essentially. Okay. So this is example 1. Example 2 I mentioned as a double exponential distribution. So this is sometimes called the Laplace distribution. All famous names here. Third example is, again, I mentioned yesterday. So this is uniform distribution. So it's a box, basically, flat distribution over a box. So this is a Heaviside theta function. So this is uniform over the interval . Theta function means that this is 1 if the argument is bigger than 0 and 0 if the argument is less than 0. So you can see that this is, it has a shape minus L naught to plus L naught, and the height here is 1 over 2 L naught. Fourth example is the Cauchy distribution. This is again normalized. So this is called the Cauchy. So unlike this, so here you see that this is sort of going down very fast, Gaussian. This is also going down fast, exponential. This is very fast because it's a bounded distribution. But this guy here is decaying like 1 over x squared. So it has a fat tail. It's pretty broad distribution. And then finally, one example I mentioned is the lattice random walk, which is with the lattice constant L naught. So that means the particle jumps, this guy means that with probability half, you get L naught, and with probability half, you get L naught, and with probability half, you get minus L naught. And so this is the lattice, well, it's not lattice random walk, it's just a delta function jump, basically. Let's call it delta. Okay, so now typically, when you have a random variable distribution like that, it's very useful. I mean, the probabilists call it characteristic function, and physicists call it Fourier transform. It's the same thing. So you define the Fourier transform of your PDF. So why do we need the Fourier transform? We'll see in a minute. So if, for example, I mean, all these examples that we looked at, in this case, the Fourier transform of that guy, Gaussian distribution, is also a Gaussian. For the double exponential, there is a Laplace distribution. This Fourier transform, this function here is Lorentzian. Fourier transform of the uniform distribution sine. Okay. Fourier transform of Cauchy distribution. Gaussian, Laplace, uniform. For the Cauchy distribution, it's actually exponential minus L naught. And finally, for the delta function, this guy here, his Fourier transform is cosine of K L naught. So in all these examples, you can work out the Fourier transform explicitly. And it's useful to actually look at the Fourier transform, because we'll see later that the Fourier transform will keep on appearing. Because in many of these problems, it's a linear equations, so Fourier transform is a natural way to look at it. Sorry? Which one? This guy? This is e to the power minus L naught modulus of K. So because you see this guy, in some sense, these two are, so if you have a, something which is decaying like exponential mod x by L naught, then its Fourier transform actually has a power law decay for large K, okay, which is this guy here. On the other hand, if this guy in a real space, if it has a power law distribution like 1 over x squared, its Fourier transform gets localized in the, K space, momentum space. So there it's e to the power minus L naught mod K. Okay? So their Fourier transforms are dual to each other. So why is this Fourier transform important? So this is because, for any characterization of any PDF, one defines a set of observable which are called moments and cumulants. So moments, for example, the kth moment, or nth moment, if you like, nth moment of a distribution is defined like so for instance, m equal to 1, first moment is just the average value, m equal to 2 is the second moment, and so on. So this is the moments, and if I know the Fourier transform, I can make a power series expansion in small k. So just expand this guy in Taylor series, and then immediately you see you can write down this as right, because this guy, when you expand in power series, you get ik to the power m by m factorial times x to the power m, and x to the power m is just a moment, mth moment. So therefore, if I know the Fourier transform, I can expand in small k, and from this power series expansion, I can read off the different moments of the distribution. Okay? And cumulants are also another set of observables which give you an idea of the shape of this curve. So cumulants are defined like you take a log of the Fourier transform and you expand in power of k again. And these coefficients, they are called cumulants. Okay? And you can see that they are related to each other, because if I take a log of this guy and I just expand, just in powers of k, so I'll get the cumulants. And so cumulants and moments are related. Sorry, yeah, you're right. So for instance, I mean, the first cumulant is just the first moment itself. Just by expansion, you can check. Second cumulant is what we call variance. This is just expectation value of x squared minus average x squared. So therefore, this is just the variance. So it tells you, how, if you have a distribution, let's say first moment is 0, so PDF is something like that. So, square root of the variance, square root of C2 gives you an idea of the width of this distribution. Fluctuation, how much it spreads around its mean value. Similarly, you can write down C3, which is so often you will see that people, when sometimes they may not have a good idea of the full distribution, but maybe sometimes you can calculate the moments or cumulants, and that gives you a good idea of the shape of this distribution, even though you may not know exactly this function. Okay? So let's look at one example again. So let's look at the example of Gaussian distribution. So that fx is 1 over square root of 2 pi L naught square. So in this case, as we saw there, Fourier transform itself is Gaussian. So you can calculate the moments easily. So mu1 is of course 0 because it's symmetric. Mu2 is L naught square. Mu3, all the odd moments vanish. Mu4, 3 L naught 4, etc. And what you see is that if I now take the log of this guy, so you see, what you see is that only the second cumulant survives. The only power of 2 is non-zero. All the others are 0. Okay? So for Gaussian distribution, all higher moments, so C2 is just L naught square. So this is the variance, if you like. The mean is 0 and bi-identically here in this example. And all the higher moments, C4, C5, C6, etc., they are all identically vanished for. So Gaussian distribution is a very special case. In fact, it turns out to be the only distribution for which all higher cumulants beyond 2, they all vanish. Okay? So that's a good way to determine, how close your PDF is to the Gaussian. So you just compute the higher cumulants and see if they are non-zero, then that means it's very far from Gaussian. If they are all identical or very close to zero, then you can see this shape is roughly Gaussian. Okay. The next thing is that knowing the Fourier transform again is quite important as we are doing the small k expansion, the small k behavior. You will see why these are important later on. So we are again thinking of symmetric distribution. So f at k as k goes to 0. So of course at k equal to 0, you see that this is 1 because it's normalized, okay? And because it's symmetric, the first term is also 0. So fk basically starts here with something, okay? The leading sort of small k behavior after 1. So that is actually very important. So for example, for the Gaussian case, as you just saw, Gaussian case, we know the exact answer, e to the power minus k square L naught square. So if I expand for small k, so f tilde k as k goes to 0, plus order k fourth. Okay, so here for the Gaussian distribution, the second term here, it starts with the power k to k square. Okay? So in fact, from this expansion here, you see that mu 0 is 1 by definition, and if it is symmetric, then mu 1 vanishes. So in general, so whenever the mu 2 exists, okay, so then you always have in general that f tilde k behaves like u2 k square over 2 as long as mu2 is finite. Second moment exists. It's a very important thing, okay? But if the second moment doesn't exist, then the leading behavior for small k is different. We'll see that in a minute. So let's take an example of this. So let's take our Cauchy distribution. So Cauchy distribution, where you have a 1 over x square tail. So the Fourier transform of that, as you saw from here, so if I make a small k expansion, the leading term will be L0 times mod k plus higher order terms. So you see here, the power is modulus k. It's, first of all, it's non-analytic. Okay. So whenever second moment, remember that in this case, in real space, the distribution was 1 over pi, and then L naught over pi square plus x naught square. Sorry, x naught square over plus L square, L naught square. So obviously, it has a tail 1 over x square. So if I calculate this second moment x square and integrate, it's divergent. Okay, so that means it's a very broad distribution, and that gets reflected by the small k behavior. In the small k, it becomes non-analytic. For anything that decays very fast, such that the second moment exists, this is always analytic function, at least for small k, and it always goes like k square. But whenever you have the second moment divergent, it becomes non-analytic. In the Cauchy case, this is 1 minus L naught mod k. And in general, if you have a power law tail, which goes like some amplitude over x to the power mu plus 1, where mu is between 0 and 2. So if mu is between 0 and 2, mu has to be positive because this is normalizable, it should be normalizable, okay? And mu has to be less than 2 because then this second moment is divergent. So then what you can show, I mean this is a little exercise, that for small k is normalized, so it's 1 first term, and the second term will be generally some L k 1 to the power mu. Okay. So if this is mu plus 1, then this small behavior will be non-analytic and it will be mod k to the power mu. This L is some constant which depends on this amplitude A. Okay, here is an exercise, just compute this L in terms of this amplitude A. Okay, so you have to just looking at the Fourier transform, and probability theory, sometimes it has a fancy name, it's called Tauberian theorem, but it's very easy to derive. So this is an exercise. Find out this constant A here, the coefficient of k to the power mu, in terms of this amplitude A. Okay? So basically what you see is that therefore the Fourier transform, the small k behavior, if it is non-analytic, then I can read off the large tail behavior of the original in the real space, the distribution. But if it is analytic, then I cannot say anything. Only thing I know is the second moment exists, but I cannot say what the tail would be. Okay? So this is an important point to understand, that Fourier transform, I mean, for small k behavior is, typically, often you hear this statement that, oh, small, large x behavior corresponds to small k behavior. But if I know the large x behavior, can I calculate the small k behavior? No, in general not. For example, if I, Gaussian distribution, you have e to the power minus x square, okay? And its small k behavior of the Fourier transform is 1 minus k square, okay? But it doesn't tell me anything about what the large k behavior would be, or if you give me this, and you ask me what is the large x tail of f of x, I don't know. I cannot say it's Gaussian because there could be many distributions for which k square, the second moment exists. Okay. So when this is analytic, you cannot find out the tail of the function in real space. But if it is non-analytic, then you can actually read off the tail, as in this example. And so for non-analytic function, particular, if it is non-analytic like k to the power mod k to the power mu, then in real space, f of x will go like x to the power whatever this exponent there plus 1. Okay. So this is an important point that, the analytic versus non-analytic behavior. Okay. So small k behavior is when you have non-analytic, power law tail, then from the non-analytic behavior of small k, you can actually deduce the large distance behavior in real space, but not for all functions. For analytic functions, you cannot say anything from the small k behavior. Okay? So this is just a sort of background, just to remind you the stories of these things. You have any question here? All right, so now let's grow from single random variable to multiple random variables, because that's what, yeah, sure. No, for the Fourier transform. Fourier transform, small k behavior. If you detect some small k, like for example log k, 1 minus log, or mod k to the power mu or something, then from that you can always figure out what the tail of the function is in the real space. But if it is analytic for small k, then you cannot say anything about the tail. Okay. Somehow it's not stressed very well in the usual when you are taught Fourier transform, but this is a very important fact. I mean, as a simple exercise, I always, teach in my class that, suppose I give you this. Yeah, I mean this. Let's say I give you the Fourier transform. I give you a function like this, okay? Of course, you can exactly integrate it and find out this Gaussian. But suppose you don't know this, okay? Can you deduce the tail of the Gaussian distribution without really carrying out the integral, okay? Just with small k behavior. You cannot, not easily. I mean, there are tricks to do that, but it's not simple trick by analyzing the behaviors near small k. Okay.
So, the thing is, if you know the Fourier transform, then of course you can correlate them.
That's right, exactly.
Without doing that,
No.
guess it from the small k behavior.
No, you cannot. Yeah. So now we look at multiple random variables. Because remember that this was our basic things, that we had a sequence of random variables x1, x2, x3, xn, etc. These are my entries of my time series. So for multiple random variables, you have to define not just its distribution, but you have to define the joint distribution always, because they may be correlated. Okay. So if you give me the joint distribution of these multiple random variables x1, x2, x3, xn, so first thing you define what is called the marginal distribution. Again, you know about this, but I'm just reminding you. So what is a marginal distribution? So marginal distribution is defined, it's like saying that, okay, if I fix one of the variables and integrate over the others, then what is the distribution of this? So I have this x1, x2, x3, whatever, you have a big time series, and I want to know, think of this as a time, and I want to know at time n, what's the distribution? If I forget about all the other things, I don't know what they're doing, but I just locally measure this guy here, and I just draw its histogram, okay? So this is the, I'll call it Pnx. So this is the probability that xn, so this is probability density of xn, okay? So this is my xn. So I don't want to know what the other guys are doing. I just focus on this guy, and I measure locally the histogram of that, and this is called the marginal distribution of the nth guy, if you like. Or if you're thinking in terms of time, like random walk, for example, this is the probability distribution that the particle is at x at step n. Okay, so this is very generally, if you know the joint distribution. So you fix the nth guy to be x, and you integrate over all the other guys. Okay. So fix this guy at x, because I'm asking what's the probability that this guy has value x. So I just have to integrate over all the other guys whom I'm not interested. So this is called the marginal distribution, okay? Now for the IID model, so I said I am going to discuss two models. So IID model. So for the IID model, as I said, the P joint is trivial. There is no correlation between these guys, and they are all identically distributed. So this is just a product of P of xi. P of xi is something which you have given to me. Okay? because each variable I'm saying they're each distributed by a P of X, and they are uncorrelated. So therefore, the joint distribution factorizes into individual distributions. So in this case, this marginal distribution, if I look at the nth guy, where n can be anything from 1 to capital N. So this guy is just have to do this, just to put it there and integrate. But you see that because of factorization property, you know, all the other integrals are 1 by normalization. So I have P of X dx is 1. So by normalization, everybody is 1. So P n x is just simply P of X, right? Because you know this guy doesn't care what the other guy is doing. It's not correlated with the other guys. So therefore, the marginal distribution itself is just P of X. Okay, but this is not true when there is correlation between the particles, and then the marginal distribution will be quite different. You know, it depends on n, and it will be different P of in general. So. So this is as an example. Let's consider this our second model that we said will work out in detail. This is the random walk model. Just to remind you, random walk again. So I'm thinking of this x as the entries of my time series as the location of a one-dimensional random walker, starting at some point, you know, let's say 0, and then just jumping. And so on. So this is xi versus I. It doesn't have to start at 0, but look, it's just for simplicity. Okay. So this is my random walk. So I start at the origin, and these eta n's are noise or increments they're called, and they are distributed each of them independently from step to step by f of eta. So f of eta is the distribution of the noise, not the distribution of xn. So the joint distribution of the etas, the noise at each step, you know, they factorize, I mean, up to n steps. So they are basically a product of f of eta I. But that does not mean that the x's are uncorrelated. So if I want to calculate the joint distribution of x1, x2, x3, xn, so we are making a change of variables. So from knowing this distribution of the noise, I can calculate easily the distribution of x's. And this is just a change of variable, right? Because you are going from eta variables to x variables. And as you can see from here, the d xn, the eta n, there is just 1. Okay? So the Jacobian of this, you know, you are making change of variables from so change of variables from eta n to xn. And the Jacobian is just diagonal, it's just change of variable, because xn does not involve any of the other etas, it only involves eta n. So the change of variable Jacobian is just 1, and therefore, you know, if you like, is the same as the joint distribution of the etas, which is f of eta I. So therefore, since because of this fact, the Jacobian is 1, so P joint so then they are normalized, but you can see that, you know, this is totally a, you know, it's a in terms of the increment, these are uncorrelated, but in terms of actual positions, they get correlated. You know, this is not a factorization to distributions of xi's, but rather the difference between the xi and xi minus 1. Okay. So now, this example is already non-trivial. If I want to calculate the marginal distribution of xn, right? That means what is the probability that the nth entry, or if you like the position of the walker at step n equal to x, right? And this is, so so what I'm asking is in terms of the random walker, that is suppose that, okay, in general this could be x0, you start from x0. You're asking what is the probability that at step n I arrive at some position x here. Okay. So this is just the propagator so this means the probability density to arrive at x at step n starting from x0. Okay. So marginal distribution of the nth entry is exactly the Green's function. So this is sometimes in physicist language we call it Green's function. Or sometimes it's called propagator. Okay. So we want to calculate this propagator for this process to calculate the marginal distribution. And before we do that, so one property which is very important for random walk, and this is the reason why random walk many properties you can calculate, that this is actually a what is called a Markov process. So what does mean Markov process? So Markov process means I have a stochastic process, and if I want to make a local jump at step n, it does not depend on the previous history. It only depends locally just at that point. I mean, for example, here, when the walker is at step n, so he's just drawing a random number, noise, and jumping. It doesn't remember anything about the past history of the trajectory. Okay? So any process that does not remember the past history so such a process is called Markov process. You can see here, so at step n-1, I'm going to jump, and the jump, I mean, this local jump, it does not depend on the previous positions at all. Okay? So what is, let's think of an example of a non-Markov process just to counter this. Simplest example is just, if you again think of this recursive procedure, let's say, this is just an example. Suppose you construct your exercise from this, instead of this, you just construct it from this relation. Okay? So here you see that the xn, current location, it depends not only on the previous time step, but previous two time steps. Okay? xn minus 2 and xn minus 1. So this is called two-step Markov process or non-Markov. This is non-Markov already because it depends on not just on the previous location, but the one before the previous location. Okay? So this is an example of a non-Markov process. There are many such examples, and you will see in a minute that why the Markov property is very important, because the moment you have a non-Markov process, calculating any path properties like this Green's function and things like that becomes much more complicated. So this Markov property, where it depends, the noise is only local and it does not depend on the previous history, that actually helps quite a lot in calculating these kind of propagators. Okay, so let's see how to calculate this propagator then. So for this, so I want to calculate g of x, x naught n. What's the probability of going from x naught to x in step n? Okay, that's all. So for this, you can actually write down, again using this Markov property, a recursion relation, and there are two types. Okay, let me first write down g Okay, so this is very simple to understand. So g of x, x naught n, I go up to step n, okay? So suppose I know where the particle was at step n minus 1, okay? So what is the probability of propagating from x naught, and let's call this guy as x prime, okay? So at step n minus 1, I was at x prime, so this is the probability for that. And once I've reached there, then I just make a jump from x prime to x, and this jump is a local jump, and it's a, this is just drawn from this f of eta. So eta here, jump is x minus x prime. And I take a product here, and that's the Markov property, because, it does not, this jump here does not depend on the previous history. So if I know this, if I condition that the particle was at here, at step n minus 1, this jump does not depend on the previous, it does not remember anything about the trajectory, what happened before. And therefore, we are using the Markov property here. And then you have an exact recursion relation, and you start from the initial condition that at n equal to 0, what's the probability that starting at x naught you will be at x? I mean, clearly it will be 0 for x naught equal to x naught, and since it's normalized, it has to be delta function. Okay? So this equation here, okay, this is called the forward Kolmogorov equation. Why forward? Because we are looking at what happens at the last step, by changing the forward position as a variable, basically. Okay? Now you could write down an equivalent equation, which is called the backward Kolmogorov equation. Sometimes one is more useful than the others. And this goes by this following. So I write for the same object, yeah, I forgot to mention, of course, then this position can be anywhere, so you have to integrate from minus infinity to plus infinity. And starting from, again, the initial condition. So what is the interpretation of this guy here? So again, think of your trajectory. You are arriving at x at step n, okay? Now, instead of looking at the forward, what happened at the last step between n minus 1 and n, let me now look at what happens in the first step itself. Okay? So suppose that it moved from x naught to x naught prime. Okay. So then, this part is just f of x naught prime minus x naught, because this is the initial jump that you choose from f of eta. So you go from x naught to x naught prime. But then after that, starting at x naught prime, you're asking what is the probability, the remaining steps is n minus 1. So starting at x naught prime, I want to arrive at x at step, in steps n minus 1. Okay? So here you are splitting the trajectory into the first step and the rest. So that's why backward, because you are varying the initial position, not the final position. Okay? So backward means you are varying the initial position. Initial position is a variable here. Okay? And forward means you are splitting the trajectory from 0 to n minus 1 and then one step further. Okay? So both are equivalent. You can sometimes this is useful, sometimes that is useful. We'll see some examples later. And but basically this is, you can either solve this or that way. This is the equation, and you want to solve this equation. Okay? So how do you solve this equation? Again, you'll see that because it's a linear equation, and you see here you have a convolution structure. So a natural thing of linear equation with convolution structure is to take a Fourier transform. So I define this g hat k x naught n as g of x naught n. Okay? So I multiply this guy by e to the power I kx. I'm doing the forward equation now. E to the power I kx and integrate over x. And then immediately, because of the convolution structure, when you multiply this guy by e to the power I kx, you can write this as e to the power I k x minus x prime plus x prime. And you associate this guy with this guy and x prime with this guy. So immediately you see that this is okay. So in the Fourier space, it becomes very simple. So it's at step n is just step n minus 1 times f hat k. And if I iterate again and again up to step n, and the initial condition is this guy delta function. So the Fourier transform of the initial condition is just exponential I k x naught. So what you get is okay. So now I can invert this Fourier transform. So inversion is, if your real space goes dx, the inversion Fourier space goes from with a factor 2 pi and with a negative sign. So this is the exact Green's function. So if you give me the noise distribution, then in principle, you can write down this exact solution like this. But of course, what you see is that it's not always easy. I mean, for some cases, like for the Gaussian, f hat k is simply e to the power minus k squared. So you can just put e to the power minus n k squared, and you can inverse the Fourier transform, and you can calculate the Green's function explicitly for any n. But for a general f of k, it's not easy to do this integral. Okay. For instance, I mean, if I give you, the uniform distribution, it will be the Fourier transform is sine k by k, and then you cannot do this integral for arbitrary n. Okay. But in principle, you have the exact answer. So let's try to analyze then what happens for large n for general fk. Okay? So here, hard to evaluate explicitly but we want to know, typically, in many applications, you are not always interested in finite n, but you want to know what happens for large n. Okay. So can we extract the large n behavior? So I'm asking at long time, after a long time steps, where is this particle likely to be? Okay. What's its distribution? So for large n, you can do an asymptotic analysis of this integral. So how do we do this? So I first write down this as n log f hat k. Okay. And what you see is that f hat k, like for example for the Gaussian case, is just e to the power minus k squared. So log of f hat k is just minus k squared. So in general, this is a negative number. So if you naively take n goes to infinity limit, this will become 0. I mean, which is sort of normal, right? So for any finite x, it will go to 0 basically. Okay. So you have to do scaling, and this is very important in physics. So basically for large n, the most dominant contribution to this integral will come from the region when this log f at k is the smallest, right? So which means that the k must be close to 0. Okay. So then I can just use an expansion, and you see why this was important to do this small k expansion of f at k. So remember that log of f at k, we had this cumulant expansion, and the leading term was this, since it's symmetric, from C1 is 0, so leading term was mu 2 k square by 2. Okay. This was the minus. So therefore, I mean here, so basically, just use f hat k as 1 minus mu 2 k square over 2 plus higher order term. So when you expand log of this and expand for small k, the leading term, if the mu 2 exists, will be this. So let's look at the case when mu 2 exists. Then this will be the leading term, and then there will be term of some constant times k fourth plus blah blah blah, etc. So what you see is that when I take the n goes to n large, I have to rescale k such that n k square remains finite. Well, otherwise, everything will go to 0. Okay. So therefore, the correct scaling is that n goes to infinity, but k should go to 0 such that n k square is fixed. How do I achieve that? So to operationally do this, so what you do, because you call it k root n as q, change of variable. Okay? Just make a change of variable from here. So under this change of variable, k equal to q root n, q by root n. Then I have 1 over root n which goes out. Okay, this n k square is q square. Now this term here, this is n times k fourth, and k fourth is q fourth over n square, and you can calculate the higher order terms, etc. And then I have e to the power minus I q, k is q over root n, so I just write it like this. Okay. So now if I take the n goes to infinity limit, but keeping this x minus x naught over root n fixed, let's call it y. So I take x to be very large, x minus x naught, n to be very large, but keeping this ratio fixed, okay? And then, you know, all these terms are negligible because it's order 1 over n, next one will be order 1 over n square. So in the n going to infinity limit, they all disappear, okay? So therefore, what you find in the large n limit, you have a very simple expression okay? All the other terms have dropped out. But this is just a Gaussian integral, so you can do it explicitly, and the answer is so as long as mu2 is finite, so what you see from these things that this Green's function in the large n limit and with this ratio fixed, okay? So the statement therefore is that the g x naught n, the propagator, in the limit when n goes to infinity, x minus x naught goes to infinity, but keeping the ratio fixed, it goes into a scaling function which is precisely 1 over, okay, if you like, 1 over square root. Actually, I should say here that this is, yeah, I mean, sorry, I mean, there's an n there, right? So 1 over square root of n into some function, let's call it f, let's call it L. For some reason, I call it L2, some function basically, okay, of x minus x naught over square root of n. Okay, you can scale mu2 also with it. Where the scaling function L2 of y is just simple Gaussian. So as long as mu2 is finite, your Green's function in the long time limit, it sort of reduces to a scaling form like this, where this scaling function is just a simple Gaussian. Okay? And this is what is called the central limit theorem. Central limit theorem usually is stated in terms of the sum of random variables, but you see, this x minus x naught, x is the position after n steps, right? And you know, we have this random walk thing, which was xn minus 1 plus eta n. So that means the position after step n is just the sum of the individual noises, right? Just the addition of these noises. So essentially, so this guy here is just sum of eta I goes from 1 to n. And these eta i's are independent random variables, and therefore this is just a sum of random variables. So what it says is that the sum of random variables, if I divide by square root of n and keep that fixed, then this random variable, that is a scaled sum, it converges to a Gaussian distribution, and that's the statement of the central limit theorem. Okay? So this is just a proof of that. Now, I'll just finish and then you can take a break. Now, this is when mu2 is finite. What happens if the mu2 is not finite? So, for example, if you have a Cauchy distribution where f of x, remember, was 1 over pi times L naught divided by x squared plus L naught squared, which means its Fourier transform was exponential minus L naught mod k. Okay? So mu2 is infinite in this case. So central limit theorem doesn't hold. Okay? So in general, as we said, that if f of x has a power law tail, noise, where mu is between 2 to 1. Mu equal to 2 means second moment exists, and mu less than 2, it means that second moment doesn't exist. So if your noise are distributed like that, then the position xn, so these are called, as I said in my last lecture, these are called Levy flights. That means you are making very, very big jumps, okay, each step. So in that case, so I have to, analyze the same object here. But now you see that I said before that f hat k for small k in such cases goes like 1 minus some constant times k to the power mod mu. Okay? So therefore, all I have to do is instead of this here, I just take, so I take a log of that, so it will be minus L mod k, plus again some higher order terms, and then I have to take a Fourier transform of that. So again here, like in the Gaussian case, you see that the correct scaling, if you're taking the large n limit, you should take the k goes to 0 limit, but keeping n k to the power mu as a fixed variable q. Okay? And if you do that same exercise as we did for the Gaussian case, just instead of mu equal to 2 here, you just have a general mu between 0 to 2. And then if you just do the same exercise, what you find is that this will be that's why I wrote L2 here, because that was the Gaussian case. And here you have a scaling variable, which is x minus x naught by L n to the power 1 over mu. So the scaling will be not square root of n as in the usual diffusive scaling, but it will be like n to the power 1 over mu. So it's because the spread is very far, actually mu is less than 2. So it's much more than diffusive scaling. Huh? Sorry, yeah, right. So, and then where this function L mu of y is just dq over 2 pi. I mean, just make the scaling, and then you'll find that this is simply the Fourier transform of this function. So in general, it's not easy to calculate for general mu explicitly this function, but special values like mu equal to half and 1/3, you have explicit expressions in terms of Bessel functions and so on. But in general, this is what is called this statement. This is the analog generalization of central limit theorem for mu equal to 2, and this is generally called the Levy-Stable theorem. So that means if you sum up random variables that have a power law tail, then the sum, once you scale it by n to the power 1 over mu, it converges to this particular distribution scaling function, and this is what is the Levy-Stable function, L mu of y. Okay? And mu equal to 2 is just the Gaussian case when the second moment exists. Okay? So this is just a generalization of Gaussian distribution, of central limit theorem, if you like, the Levy-Stable law. Okay? I think we can take a break now, and then we come back, and I just want to do one thing, and then we'll go to extreme value statistics.
then the others, okay, okay, I not missed that. Okay, so I just understand. Then you those go to 0 because now, of course, k small k doesn't make any sense. You're under the integral, right? So all k's have to be taken into account. It's not a small k expansion. That's what was confusing. So it's just these are other terms that are there from other. So it's just that it's a positive of Gaussian.
Yeah, like
Of
for instance,
Gaussian.
the exponents.
No, the levy won't be of that form.
Like for instance, exponents. Use of formulas.
I mean,
Okay, drawn from that. Always drawn from exponents.
huh.
So then that has less exponent. To write down exponents plus something, you can also
Yeah. Meaning, if f of k is not in Gaussian, but it is something plus Gaussian times something else, right? Then you can write it as an expansion. But it's an exact expansion. So tomorrow you take just a cumulative expansion. Okay, fine, I understand. So you can write the log of f. Oh, right, because you know to just log f is a cumulative.
Yeah.
So it's just a cumulative expansion, and then in that, then you notice that in the logarithm limit, that's how algebra is.
Yeah.
Because I'm still trying to figure out what
So
you said.
basically, plus k and k square is all
And
x.
and k squared is
Then the k to the power 4 will be basically q of n k plus 4, but then
yeah.
q plus 4
So
by
mine I'll have to just look at it. I just kept looking at the first thing. What were we talking about? He's talking about off Gaussian. Basically any cumulative expansion. Log of f. Yeah, okay. I forgot. Didn't catch that. Does anybody have a full chapter? Let me ask.
Okay, so I want to do one last thing, which is, so we are talking about the central limit theorem and random walks, right? Now all of you of course, are familiar with Brownian motion. So what's the connection between Brownian motion and this random walk thing, okay? Because random walk is occurring in discrete time, whereas Brownian motion occurs in continuous time. So how do I get from the random walk to the Brownian limit? Okay, so this is the continuous time limit. So once again, we start our favorite random walk model like this. And I'm going to assume that these are IID variables drawn from f eta such that the mu2 or sigma square if you like, second moment, exists. So this is what we are calling mu2. So it's finite. So that the central limit theorem holds for the propagator. Okay? So then as I said, the xn is summation eta I equal to 1 to n, just iterating this equation. So this is a sum of independent random variables. So if I calculate now the variance of the position itself, xn square, so this will be ij but the eta I, eta j, they are independent noise when I is not equal to j, right? Eta i's are independent. So therefore, this is just local eta square times delta function of I comma j. Right? When I is not equal to j, this is 0. So you see that this becomes just n times this eta square average, which is sigma square. So the fluctuation of the position at the nth step, so if I look at this, the variation, the variance of this is simply n sigma square, okay? If this mu2 or sigma square is finite. Okay, so now if I want to take the continuum limit, time limit, so time means that you write, if your actual time is real time, and then you say that, okay, delta t, so if I want to discretize this time, so this is my real time, I want to discretize in steps of delta t to make connection to the random walk. So therefore, you would write down t as delta t times n. N is the number of steps, and delta t is the duration of each step, if you like. And this is my time. So therefore, if I want to write this in terms of the real time, I just want to replace this n by t over delta t. So what you see is that the variance, therefore, is proportional to t, but with a factor here sigma square by delta t. Now, if I take the delta t goes to 0 limit, keeping sigma finite, then clearly, this is going to diverge. It makes no sense. So if I have to make a sense out of it, to have a proper continuum limit, I must take the limit delta t goes to 0, but sigma square also going to 0, such that their ratio remains fixed. And this ratio is what we write down as 2d. So therefore, you have to rescale always. Sigma square has to be rescaled as 2d times delta t. So the noise, if you like, noise variance must be proportional to delta t and not delta t square. So this is the famous Einstein's Brownian motion scaling, right? So then you see that x square is just 2 dt, and this d is called the diffusion constant. So then you have the x square average going like 2 dt in this continuum limit, And this is this famous diffusive law of Einstein. So, and now can we write down this Markov jump process that we had also in a Brownian motion language, continuous time language? What's the continuous time analog of this discrete jump process? Okay. So for that, you just write down this as, so this is your delta x, jump, which is this eta n. So let's divide by delta t. So that's eta n by delta t. Okay. Now I want to take the limit delta t goes to 0. And then, this object, let's write it down as eta evaluated at t. So this is my rescaled jump, basically, or noise. So what's the property of this guy? So its expectation value, of course, is 0. It's a random variable. Expectation value is 0 because average eta is 0. What about its correlation function? Eta t prime. So eta t prime, that means you are looking at two different times, right? So which means that you are looking at two different jumps, nn and nm. So this will be basically 0 because they are independent, okay, if t is not equal to t prime. However, if t equal to t prime, then you see that this guy, eta square of t, by the definition, this is eta n squared by delta t squared. Now, what is eta n square? We just said eta n square is just sigma square over delta t square. But sigma square we have rescaled already as 2d times delta t. So therefore, the whole thing behaves like 2d times delta t. So in the continuous time language, the noise at a given instant, eta square of average t, it actually diverges as 2d over delta t. Okay, so if you go to the continuous time limit, so then what you see is that this guy, dx dt, you can write it like this. So this is what is called the Langevin equation of Brownian motion. This is a definition of Brownian motion. But the noise, or Wiener process in mathematics is called, but the noise is such that its average is 0. It's uncorrelated at two different times, but this is continuous time. But the local variance is infinite. So therefore, what you write is, one way to write this noise correlated in continuous time is 2d times delta function of t minus t prime. Because delta function means when you integrate, multiply by dt, when you integrate it's 1. And you see that this variance here, when you multiply it by delta t, it's actually constant 2d. So therefore, you see that this delta function is basically 1 over delta t behaves like this delta function. And such a noise, so this is what is called the white noise. White noise means it's uncorrelated, and exactly at the same point, it's of course divergent, but divergent in the sense that it's integrable divergence, and therefore you write it as a delta function. Okay? So this is the famous Brownian motion, and then from this you can write down xt. If you integrate, if we stay saying that x0 starting from the origin, so you have eta tau d tau, and if you again calculate x square of t from this, which is 0 to t eta tau 1, eta tau 2, d tau 1, d tau 2. You use this property here, and you get 2d And this, you can check that this will be exactly 2 dt. And if you take at different times xt prime, that will be 2d minimum of tt prime, which is the standard property of a Wiener process. And so, to see in this equation here, for example, the forward Kolmogorov equation, what does that become in the continuous time limit? So to do this, I mean, remember that this was x prime, so the discrete jump can be a big jump, but when you go into the continuous time limit, when delta t time step is very small, so this jump is also very small, right? So we have this dx, so delta x, what is the jump? Delta x is therefore eta t delta t, right, from this equation. So I can write down this as g x x naught now in time t. That means at the previous time step, I was at x prime, and x prime is just x minus delta x. So that means x minus eta t delta t. So I was there, and then I made a small jump by eta t delta t, and I arrived at x. Okay. So this is comma x not comma t, and then I have to multiply this by the distribution of this noise f of eta, right? Because you're jumping, now this jump can be anything, is drawn from this f eta in general. And so this is the sort of continuous time analog of the Kolmogorov equation. F eta means this noise here, okay, I just replace this t there, eta delta t. Eta is the noise, instantaneous noise at time t. And now what you do is you just do a Taylor expansion of this guy. So when I do Taylor expansion, it will be g x x naught t minus eta delta t times f eta d eta, so it's expectation value of eta, times del g del x. And then I have a second term, which is eta square delta t square by 2 plus order delta t cube. Now, jump distribution, average eta is 0, of course. Okay. And we have just seen that eta square expectation value, this guy, is 2d over delta t, right? Remember from there. So therefore, I take out this on the left hand side. Sorry, this should be t plus delta t. Yeah. And if you write this as t plus delta t. Yeah. So I take, so the first term, g here, f eta is normalized to 1. So therefore, when we do the integral, you essentially have g x x naught t. This term is 0 plus d delta t square. There is a delta t square and there is a 1 over delta t. So it becomes delta t times d2g dx square plus order delta t square. And now I take this guy to the left hand side. This is g x x naught t plus delta t. So if I take on the left hand side and divide by delta t and take the limit delta t goes to 0, then you arrive at the continuum equation. And this is, which is starting from the initial condition so forward Kolmogorov equation becomes just a plain diffusion equation, or the Fokker-Planck equation associated to this Langevin equation. and this d is the diffusion constant. I mean, those of you, I mean, you should read, if you have not read it, Einstein's original paper in 1905 on Brownian motion. This is exactly how he does it. A beautiful paper, so please read it, I mean, if you can get to do this. I mean, he does it exactly by this method, okay? And starting from a discrete random walk and jump process, and then how you arrive at the diffusion equation, okay? So, and diffusion equation, you can easily solve this again. So by Fourier transform, so if I define again g x naught t as then you immediately see that in the Fourier space, different modes get decoupled, and you have that equation, solve it trivially. And then you invert the Fourier transform. It's just plain Gaussian, as it should be. So continuum limit, of course, is much more easier, as you see that, you know, the Green's function, it has this, and this is again due to central limit theorem, because large n limit is like the, you know, when you take the continuum, you know, you see this t equal to delta t n. So, you know, taking the delta t going to 0 limit is like n is t over delta t. If you keep t fixed, that's like taking large n limit. And therefore, you would expect by central limit theorem that you would come to Gaussian distribution. And that's what you find. But the main point I'm trying to say here is that the forward Kolmogorov equation, often, you know, you saw the exact expression of the solution in terms of the jump distribution. So jump distribution is, you know, it depends explicitly on the jump distribution. But there is a universal limit as long as the sigma square is finite, that is, the second moment is finite, that in that limit, in a long time limit, it somehow converges to this Brownian motion or diffusion equation. Of course, if sigma square is not finite, then it will not, you won't be able to write down a simple equation like that. And people have worked on the continuous time limit of Levy process, but, you know, essentially you have to solve really this full equation itself, okay? But as long as the second moment is finite, you get back to the diffusion equation, and then things become simple. And similarly, you can work out the backward equation also. So, you know, same thing, I mean, I erased it, but the backward equation would be backward diffusion equation. That means del G del T will be D. And again, if you solve by the Fourier transform, you will get back the same solution. So you can either solve it by forward method or by backward method. Both are equivalent. And you get the Gaussian solution. Okay? So the main thing that we learn from here is that for any Markov jump process with a finite sigma square, if I take very large n after a large number of steps, so any Markov process with a finite sigma square, okay, in the large n limit, it always converges to Brownian motion, or mathematicians call this Wiener process. It's not a really physical Brownian motion, because this is dx dt equal to noise. Okay? So when I say Brownian motion, I mean just dx dt equal to white noise. Because real physical Brownian motion, you have momentum and other things, so that also over damped limit, it becomes the Brownian motion like this. But this is the statement. Okay. Okay, so this was, I mean, all this is just a basic recap of, very basic knowledge of random walk and central limit theorem and random variables and so on. Took me some long time, but it's worth doing it because it's important to understand this before we proceed further. So with this basic background, so now we will move to extreme value statistics. And I want to again solve two models. You will see that for IID variables, again, it's very simple to calculate the distribution of extreme, maximum, for instance. But for random walk, for a jump process, it's very, very, very hard, okay? Except in the Brownian limit, again, if you work in the continuous time limit, then the distribution of extreme, you can compute it explicitly. We'll do that in the class next lecture. But for general jump process, it's very hard problem. So in other words, the moment you have correlations, that really screws up things. I mean, it's not easy. Okay. I'll start today. We will not finish today, but we will continue in the next lecture. So now I come to the extreme value statistics. So once again, the basic picture, I have entries of a time series, xn versus n. And so there is a joint distribution. We have total number n entries. And I want to calculate the distribution of, let's say, the maximum or alternatively minimum also, similar behavior. So I want to know what is the distribution of this x max. I should use the same notation, otherwise I keep changing notation. So okay. So this is the PDF of this random variable. That means probability this times dx equal to probability that x max takes the value x between x and x plus dx. Okay. Just a PDF, okay. If you don't forget about all this. So P max and we want to compute this object. Okay? And as I discussed last lecture, that it's easier to compute the cumulative distribution of x max which is defined as, I was defining with a W in the last lecture, but it's the same thing. So that means what's the probability that the maximum is less than or equal to x? Okay, so this is the and if I know the cumulative distribution, I can just take a derivative with respect to x, that gives me the PDF. But nice thing with this object is that if you know the joint distribution, probability that x max is less than x is the same as the probability that all of them are less than x. So you have a indefinite integral going from minus infinity to x. So this x was, remember, the hard wall that we discussed yesterday. So that means I'm asking what is the probability that all of them lie to the left of x. Okay? So that's the exact formula for any joint distribution. And now the question is how to analyze this. Okay? So as I said, I'll discuss two models. First model is the IID model. And the second one is this random walk model. In the IID model, the variables are uncorrelated, and the random walk model, they are very correlated, as you saw. So let's start with the IID model. So in the IID model, we know that the joint distribution factorizes into individual distribution. And individual marginal distribution, I call it P of x. Okay, so P of x is given. And is normalized to 1. It can be anything from minus infinity to plus infinity, whatever, any arbitrary distribution. And then, as we explained, that if we now use this, this factorization property, this whole thing just reduces to because there is no correlation, so the full partition function factorizes, and we have the exact expression. This is exact for all n. That's the exact answer. So, for example, if you give me exponential distribution, positive exponential variable, so suppose that you give me this. So they are positive random variables, but each of them is distributed exponentially, normalized to 1. So then you see that the cumulative distribution of the maximum. So if I do this integral, so this will be now from 0 to x. So if you take n equal to 1, 2, 3, whatever, you get the exact answer for the cumulative distribution, and taking the derivative of that, so P max therefore okay, you can plot this PDF and watch it. You should do it, this exercise. But then the question is, okay, you look at this guy, and it depends on the P of x that you put in as your input. Okay, so it depends very much on this P of x, and so naturally physicists are always looking for universal behavior. So for instance, when I discussed in the previous first half of these things, we are talking about central limit theorem, which says that if I take n independent variables and I sum them up, and then if I scale by square root of n, then no matter what the individual distribution f eta is, as long as the second moment is finite, I always converge to Gaussian distribution. That's the statement of central limit theorem. Is there any analog of such limiting laws in the case of extreme value statistics? Okay, that's the question we're asking. So what you would expect, like in the central limit theorem, that if you take the n to be large, that maybe it might actually converge to something, some universal distribution which does not depend on the details of Px. Okay, so we're searching for universality. Because if there is no universal behavior, it's quite boring, because then for each thing you have to do it separately for each distribution, and it doesn't tell us any general law basically. Okay, so we're asking just as a sum of random variables divided by square root of n in the long time limit converges to a Gaussian distribution. So this is the central limit theorem. Is there any sort of similar analog when we look for large n limit of this functional form? Okay. And let's see, let's again work with the example before we go to the general thing. So let's look at the simple exponential thing. Okay. So we have the exact answer here. Now I want to take the large n limit. Okay. So to take the large n limit, what you do is you first write down the exact expression n times log of 1 minus e to the power minus x. So again, if I take the large n limit without doing anything to the x, everything will go to 0. So you can't get really any behavior. So it sort of suggests that there must be some scaling. I have to, when I take the large n limit, I have to scale x in a way such that I go to a limiting distribution. So how do I do that? So clearly for large n limit, so in order that this is it has to be small in order to make it order 1 quantity. So how can it be small? If it is small only when x is very large, right? So then you see that I take the large x limit of this. I take large x and large n both. So if I expand, the large x e to the power minus x is very small, so I can expand the log. So log of 1 minus z is z minus z squared by 2 plus z cubed by 3, etc. So therefore, this becomes n e to the power minus x minus n plus n e to the power minus 2x by 2 and so on. Okay. And now, so what it says is that I should take the large n limit and large x limit, but keeping this combination fixed. If I do that, then all these other guys, they all go to 0, right? So therefore, in that limit, so x goes to infinity, n goes to infinity, keeping n e to the power minus x fixed. Then I can drop all these terms in that limit, and then I can write down this as e to the power minus e to the, and n e to the power minus x, you can write down as e to the power minus x minus log n. Okay. So what this tells you, this simple exercise, is that this exponential case, so if I take n goes to infinity, x goes to infinity, but keeping x minus log n as z fixed. So I take this large, but the difference is fixed. So in that case, my q max of x comma n, it converges in that scaling limit as some function, let me call it f1, of x minus log n, scaling function. And this scaling function has this nice form. So this is what is called the Gumbel distribution. Gumbel form, basically. Okay. It's a cumulative distribution, because when z goes to infinity, when x goes to infinity, it should go to 1, right? Because this is a cumulative distribution. When x goes to infinity, it becomes 1. So this function, if you plot, it's sort of, okay, and the PDF of that, so PDF is just the derivative, so PDF therefore, P max of xn, therefore just ddx of that, which means just fi prime of x minus log n. But this f1 prime z, just taking a derivative of this, is just exponential minus z minus e to the power minus z. Okay. So when z goes to plus infinity, you see this term drops out and it decays exponentially. So if I plot the derivative, it decays exponentially on this side. But on the other side, z goes to minus infinity when x is much, much less than log n. Z goes to minus infinity, so this guy becomes very large, and you have an exponential of a very, very negative large number. So it decays to 0, extremely quickly. Okay? So the distribution is highly asymmetric, Fi prime Z, the Gumbel distribution. This is called the Gumbel PDF or Gumbel distribution, if you like. And it is, it has this tails, okay? And on one side is super exponential tail, and the other side is exponential. So this side is decaying like e to the power minus z, because this term has become small, and this side is exponential minus z when z goes to minus infinity. So it has a very, very asymmetric tail, okay? So this, at least for this one distribution, we see that it does converge into a limiting law in the large n limit, okay? Now question is it only for the exponential, or does it hold for other cases, okay? So let's see a second example. So effectively what we are doing, as you saw in the exponential example, so I can always write, because it's normalized to 1, I can always write down this as 1 minus x to infinity right? For the exponential case, this is just 1 minus e to the power minus x. I do this because then when x is large, I'm anticipating that it will happen at the large x, large n limit. So then this becomes very small, so I can again write this as e to the power n log as 1 minus x to infinity dx prime dx prime. Just remember this example just in parallel. So again, this term for large x, this term will be small, so I can expand it. And the leading term, just exactly what we did here, the rest of the term I dropped it. So leading term will be this. So what you see, and remember for the exponential case, this was just e to the power minus x which came out. But otherwise you see that the scaling limit, large n limit, large x limit, it depends only on the positive tail of this function. It doesn't depend on the full function. It depends on what is the asymptotic behavior tail of this probability distribution. That decides the limiting behavior, okay? So let's see explicitly an example. Suppose I take this to be just a Gaussian distribution. With variance 1. And x can be anything between plus infinity and minus infinity. So this is the distribution given to me, and so I just have to evaluate this guy here. So I have to evaluate this integral here. And this is, something which is called the error function. So error function is defined like this with this normalization. And it's complementary, which is called the error complementary function, which is simply 1 minus error function of x. And this is just 2 by root pi x to infinity e to the power minus u squared du. Okay? So if you just call x prime by root 2, if you call is u, you can actually write this as half okay. And this guy for large x, so our complementary function for large x it behaves like it's very easy to derive these asymptotic properties. So this will be e to the power minus x square divided by x root pi. Okay? So therefore, what you have, this object there, where is it gone? Yeah, here, this guy. So therefore, this guy, to leading order, we can write down this as e to the power n over root 2 pi e to the power minus x square by 2 by x. So this is an approximation where I'm looking at a large x behavior and large n behavior. This is the leading behavior, okay? And so again, I mean, to get a proper limit, you have to take the large n and large x limit, but somehow keeping this guy order 1, essentially, okay? This is just root pi. So how do we write that? So again, it turns out that this quantity, they are not very important, okay? So what I'll do is, in order to search for this, so here we have seen that x is actually log n in the large n limit, plus some variable z, which is of order 1, right? So that's the scaling, basically. So what we can do to anticipate, we can just write down x equal to an plus bn times z. So we don't know what is an and bn yet, but we have to choose an and bn such that, this object here in the large n limit becomes of order 1, okay? Where z is of order 1. So if I do this, so if I just write just substitute this, so you see that this becomes n by root pi okay? And so what do I, now, okay, it turns, okay, I mean, you can check a posteriori that this guy, is small, essentially. So Bn is small, much smaller, actually, Bn will be small. We can check that a posteriori. So then, you have e to the power minus, okay, n over root pi an e to the power minus an square by 2. So that's this first term with this, okay? And then you have e to the power minus an bn z minus half bn square z square. So now, if I choose an such that this object is 1, let's say, okay? So choose there should be square root of 2 pi here somewhere. And Bn equal to 1 over an. So if I make this choice, because I'm free to choose whatever I like, an and bn, and I would like to choose them such that this object becomes independent of n. That's the goal. And if I choose it this way, so suppose I choose this to be some 1, and I choose an times bn as 1, and then you can check that, so for instance, if you solve this guy an, so this is difficult to solve for large A, but large n you can do an asymptotic expansion. So an to leading order will be square root of log n, and then there's a correction term, log n by 2 square root of 2 log n, etc. And bn is 1 over n, therefore 2 leading order is 1 over square root of log n. So bn is indeed small, And you can check that the assumptions you made in neglecting this term is correctly justified. And you can see that this guy is also small, so you can throw it away. So essentially what happens, that if I make this choice of an and bn, then in this limit n goes to infinity, it again goes into Gumbel form. Okay. So of course, in the case of exponential distribution, we have seen that an was just log n and bn was 1. Right, this is the case. An was log n and bn was 1. And here we see that an has a more complicated square root of log n to leading order of a large n, and bn is 1 over square root of log n. Okay? But the scaling function in both cases is exactly same, Gumbel distribution. Okay? So that hints at some universality. In fact, the statement is so as long as P of x is unbounded, means it goes all the way up to infinity, it has support over whole space, and it decays faster than any power law. That means, for example, you can have, its tail. So everything depends on the tail. So it could be something like x to the power delta, where this delta should be positive. It should decay faster than exponent power law. Okay? So if this happens, okay, so exponential and Gaussian both belong to this class. Here delta equal to 2, and for the exponential delta equal to 1. So for any px which has a fast decaying tail like that, then the Qmax, the cumulative distribution Qmax of x comma n, it converges into the scaling form. Where this Fiz is a universal function, and this is this Gumbel form. That is the PDF again will be just a Gumbel PDF that we drew here. So this means that this An and Bn are non-universal. They depend on the tail of P of x. But up to those so this means that the distribution, you see, x is centered around An, if you like, and it has a width around that, which is of order Bn. Okay? So if I plot this distribution, so there will be An, so raw distribution, raw histogram if I plot, so it should be the derivative of that, so that means P max it should be picked around that, around the center here, An, and there's a width of order Bn, okay? But the scaling function, when you subtract An and divide by Bn, they all collapse basically onto the same curve, and this curve is universal as long as this decays these things. Okay. Now here is an exercise. I mean, if you have a arbitrary delta, we have done the delta equal to 1 and 2 case explicitly, but you can try to show yeah. Sorry? Yeah, no. Yeah, exactly. Centered, it's some function of x minus an over bn. That means the distribution is centered around an, Not center, by centered I mean the peak occurs at AN, and there's a fluctuation around that, and the fluctuation scale is BN. Okay. So for general delta, you can show that the AN.
But it is of the same form doesn't have values.
Which form? Sorry.
That it is one, it's not symmetric about.
Yeah. No, it's the same scaling function. That's the point. Scaling function is universal. You know, it does not depend on, as long as Px decays faster than any power law, they all, I mean, An and Bn are non-universal. I mean, they depend on the actual Px you are looking at. But once you center it and scale it, that scaling function is completely universal and is given by the Gumbel distribution. Okay. So for general delta, this is An is log n to the power 1 over delta, and Bn is 1 over delta times. So you see that for the case of exponential distribution, Bn is 1. That means as n increases, the width is of order 1. Okay. So it's centered, but the width is of order 1. Whereas in the case of Gaussian, the width, which is Bn, is decaying like 1 over square root of log n. So it's becoming narrower and narrower. And what you see from this general expression here is interesting that, for there's a delta equal to 1 is a critical value. Delta equal to 1, this is 0. That means it is independent of n. It's order 1, the width. Delta bigger than 1, this is negative, which means that the width decreases as you increase n. And for delta less than 1, it actually increases. It becomes broader and broader. Okay? So that means basically, I mean, if I do my experiment, I calculate the x max, then on an average, x max will be, this scale, x max will scale like log n to the power 1 over delta in general. So for example, for Gaussian, it's square root of log n. For exponential, it's like log n. So it's not very big. Even for n big, it actually goes like, maximum only goes like log n, basically log n to the power some power. And the fluctuations around that scale, so essentially you have to remember that this as a random variable x max behaves like some an plus bn into z, and this z is a random variable of order 1, and its distribution is given by the Gumbel form. Okay. So this is this. So if I look at it as a random variable, it has a deterministic part and it has a fluctuating part. Deterministic part, the scale is this guy log n to the power 1 over delta in general, and this guy's scale, it depends is on this. So for instance, if I calculate the expectation value of x max from this relation, you get an plus bn times average value of z. Average value of z you can compute is basically it's a Euler function, Euler gamma number, Euler number, some order 1 number. And so therefore the maximum average value of the maximum scales like this an, which is log n to the power 1 over delta, plus there's some correction term here, because bn is small. Okay. Similarly, you can calculate the variance of x max and so on and so forth. But basically, you have to remember this, that x max, so just like the sum of random variables, remember that if I have a sum, so like this eta 1 plus eta 2 plus eta n by square root of n, this was converging to a random number which is distributed as Gaussian, right? This is the statement of CLT, central limit theorem. What this means is that if I look at the sum of n random variables, so in this language, suppose I say x1 plus x2 plus x3, xn, then this guy goes for large n as something into square root of n, okay? And this guy here, z, is distributed as a Gaussian order 1 number, okay? And so similar statement here it's just a order 1 thing plus shift essentially. And so this is this this is analog of the central limit theorem for fast decaying random variables, okay? So this is the Gumbel law. And in fact, there's a physical, I'll finish with that. There's a physical meaning for this an and bn. So basically what happens is that you have a basically random variable. So you have a p of x. So imagine that you are drawing the histogram of any of these random variables, p of x. Let's say Gaussian or whatever these things, okay. So x max, what do you expect? I mean, x max means, some value, that's the maximum value. That means, basically the number of guys, so what's the probability that something will be, x max will, so suppose I give you x max is x, okay. So then what is the scale of this? How do I estimate that? So scale, that means that because this is the last guy, so that means, if I integrate my PDF from this value of this last guy to infinity, so this is the fraction of particles which are here. These are IID variables, right? So a fraction of particles which are there. And what is the fraction of particles? This is just 1 over n, right? Because this is already the maximum. So only one guy is there at the border, basically. I mean, there's nothing here, okay? So this is the physical meaning of this relation that we had somewhere. Yeah. This, remember that we are writing down as e to the power minus n x to infinity px prime dx prime. We are setting this to be of order 1. So that is just saying that, from x max, x to infinity, the fraction of particles is just order 1 over n. Okay? And Bn is just these fluctuations around that. That's the. So this is the relation to estimate An. So you just scale from An to infinity. You set it to be order 1. So that gives me the scale. That what's the scale of the x max, and similarly the fluctuation around this can give me a scale of this Bn. Okay? So mean and fluctuation basically. So that's the main point. And so what I want to show you next day that if it decays as a power law, or if it is bounded, things like that. So then you have different laws. Okay. So it's not the Gumbel law. It will be something called Frechet and Weibull law. So in fact, there are 3 different types of limiting laws, which are universal limiting laws for extreme statistics for IID variables. And so that's what we'll do in the next lecture then, tomorrow. Okay, any question? Yes?
The PDF is actually asymmetric.
Can you?
The PDF
Yes.
of X max is asymmetric.
Asymmetric, right.
How can I understand it in physical or in simple?
No, but think of just again exponentially distributed variables. So you choose n random numbers, right? And you're asking for the maximum of that. So obviously maximum, is this is the point, right? The maximum is not not centered around the average, right? Whatever. I mean, even if you take very of them, you are always looking at one extreme guy basically. Okay. So that's why the extreme value statistic is different. It's a little bit counterintuitive, but it's not. You cannot think of in terms of a single PDF value, okay, or sum, for example. Okay. The extreme value, it just shows that it's not. For example, I mean, if I look at n random variables, last guy is, let's say, is of order 1, but the maximum will be of order log n to the power 1 over delta. So it's much bigger, of course. Okay, because each sample I'm choosing only a very specific. I'm biasing the sample in some sense by choosing the rightmost guy, right? So which is always big. So therefore, it has a more weight towards the positive side than on the negative side. Okay, so that roughly explains the, yeah.
The mean of px need not be 0.
Mean of px need not, no, I mean here I'm just for simplicity. So for example, exponential case, it's a positive random variables, right? So its mean is non-zero, clearly, yeah.
And for the Gumbel, for
Yeah.
the mean of
Mean of Gumbel distribution is Euler-Gramer number. So, so if you say that e to the power minus z minus e to the power minus z, right? This is your PDF. If you calculate its expectation value, once somebody wrote up to 10 decimal places, of course nobody is going to check because it was his phone number. People only remember the first 3 decimals, like.
So I guess the point is that depending on the system, you have it shifted up and the width.
Yeah, so I mean that's when depending on your px, I mean there are these two numbers an and bn, which depend on the details of px, okay. But once you scaled and shifted and scaled, that this distribution is universal. So, any other question? Okay, so then let's go for lunch. Oh, sorry.